A moving needle made earthquake records comparable because it drew while the ground moved and kept a record after the room was still. Add a clock, then another station, and that thin line can be compared across distance. The question is how this simple trace became evidence strong enough for people far apart to test the same event. First, start with the physical trick. An early seismograph used a heavy mass that did not immediately follow the motion of the ground beneath it. The frame, table, and paper drum moved with the earthquake. The suspended mass lagged behind for an instant. A pen, stylus, or tracing point marked the difference between those two motions. On a rotating paper drum, the result looked like a wavering line. That line was not a miniature picture of the whole earthquake. It was a record of movement at one place, made by one instrument, under one set of conditions. The mechanism mattered because it gave a shocker sequence. A first motion, a stronger passage, then a fading tail. Second, the paper needed a clock. A seismogram without a trustworthy time mark could be interesting, but it was hard to compare. One observatory might say its needle began to move at a certain moment. Another could produce an equally dramatic trace with no dependable way to align it. Shared time signals made those separate records comparable. A station clock and dated paper record let observers mark when a disturbance reached them. Now compare two stations. If the first small motion reached one record before the other, the gap between those marks became evidence. It did not settle every question by itself, but it let scientists test a location, a distance, or an arrival sequence instead of relying only on impressions. Third, the record became more valuable when it could travel. In the late 19th century, researchers including John Milne worked in Japan, where frequent earthquakes made the limits of casual observation impossible to ignore. Instruments, observers, and regular reports created a habit of looking at shaking as something that could be recorded repeatedly. The first mechanism was the suspended mass. The second mechanism was shared time. The third mechanism was a network willing to preserve and compare records. A paper strip in one observatory became more than local equipment once another station could read its timing and ask the same question. For example, look at the difference between an eyewitness account and a dated trace. A person in a city might report a violent jolt followed by falling masonry. That testimony tells us what danger felt like and where people ran. A paper drum might show a smaller arrival before the strongest movement, then a longer fading pattern after the room seemed still. Both forms of evidence matter. The witness carries the human stake, families, workers, and residents making decisions in seconds. The instrument carries a sequence that fear cannot be expected to preserve. Reliable sources do not ask us to choose one and discard the other. They let each kind of record answer the question it is best able to answer. The bigger point is that comparability is not the same as certainty. Early instruments differed. A pen could stick, a paper drum could run at the wrong speed. A clock could drift. One station sat on a different kind of ground from another. Scientists had to calibrate instruments, check reports, and decide which differences came from the earthquake and which came from the machine. That is why the line on paper was useful evidence rather than a final answer. What we can say is that shared methods made criticism possible. If two records disagreed, the disagreement became visible. People could inspect it instead of hiding it inside a confident story. But the story is not a simple march from ignorance to perfect science. The moving needle was an instrument inside institutions. Someone had to buy the machine, keep the clock accurate, change the paper, label the trace, mail or telegraph the report, and store it in an archive. Someone also had to decide what counted as a useful reading. This matters because records are built by systems, not by machines alone. A beautiful seismogram locked in a drawer could not help another station. A shared format, a dependable schedule, and people who compared notes made the line meaningful. The midpoint turn comes when we notice what the instrument changed about authority. A witness once had to persuade a distant reader with words. An official report could sound more certain simply because it carried a seal. A time trace gave neither person automatic victory. It created an object that could be copied, measured, and challenged. That did not remove bias or politics from disaster response. Cities still decided where to spend money, which neighborhoods to prioritize, and what risks to accept. Yet the paper record made some claims easier to check. The problem shifted from whose memory sounded strongest to whether the timing, instrument, and comparison held up. By the 20th century, seismology had expanded through wider station networks, more standardized instruments, and shared methods for interpreting records. The worldwide standardized seismograph network carried that work further in the 1960 seconds, but its logic was already visible in the old paper drum. A signal in one place gains power when another place can recognize it under the same rules. This is why a moving needle belongs in the history of communication as much as the history of earthquakes. It was not sending a message in words. It was making a physical event readable across distance. There is also a limit worth keeping in view. A trace can measure motion. It cannot by itself measure every consequence. It cannot show which resident could leave a dangerous building, which worker lost a job after a disaster, or whose neighborhood received help first. For that, we need maps, photographs, testimony, financial records, and local history. The source chain matters. An archive can preserve the instrument record, while a survivor's account can preserve what a line on paper leaves out. Trust comes from seeing where each source is strong and where it is silent, not from pretending that one graph contains an entire human event. Finally, the payoff is larger than one clever machine. The moving needle made earthquakes comparable by creating a repeatable trace, attaching that trace to time, and placing it inside a network of other records. Its consequence was practical. Scientists could test where motion began, how it traveled, and whether a new claim fit the available evidence. Its consequence for viewers today is quieter but familiar. We still trust shared measurements only when we can ask how they were made, who kept the clock, and what the record leaves out. When a line on a screen seems to settle an argument, would you look first at the line itself, or at the system that made it comparable? For more evidence-led stories like this, like the video and subscribe. See you in the next one.